what we are going to do today is to
all the way down the right way. Normally,
what we are going to do today is first to recollect very rapidly what we did yesterday, because we will need that notation again, and then we will proceed from there. The first thing we will do is to derive the generalization of the Maxwell's equations. That means we will derive the Yang-Mills equations in the presence of the Fermions that we considered yesterday. Then we will make step-by-step generalization, and hopefully today we will end up by constructing the Lagrangian of the standard model for one family of leptons. Okay, the electroweak Lagrangian of the standard model for one family of leptons. That's the aim of today's lecture, if we get up to that point. Okay, we will make a step-by-step generalization. So let's remember first we consider a Dirac spinner which also carries an SU2 index. So this transforms like 2 in with respect to the SU2, which we call the gauge group. Okay? We use elements of this group to perform gauge transformations, local gauge transformations. You understand the meaning of this notation, I assume, right? 2 means that this is a spinor of SU2. As I mentioned yesterday, I'm not going to mention the Lorentz indices anymore. I'm not going to tell you that this is a Dirac spinor for component Dirac spinor. This is assumed. And we wanted to construct an action which is invariant under transformations of this type, where this Ux is a unitary 2x2 matrix. So U dagger X equals to U inverse X. And we argued that in order to be able to do this, we must introduce a vector potential, or a set of vector potentials, where tau A are the generators of SU2 in the fundamental representation, in the two-dimensional fundamental representation. And the invariant action that we constructed was as a deceptively simple-looking form. You can also add a mass term for the psi, but I'm not going to do that. In fact, in the standard model, you will not add the mass term. You'll see the reason today. So this is the simplest form that you write for the action, where there are 2 things that needs definition. D slash, of course, is always gamma mu d mu, and d mu was defined in this way, where A is this matrix we wrote here, and F mu nu was d mu A nu minus d nu A mu minus I A mu A nu. This is as far as we arrived yesterday. Then we said that under this transformation, in order for this action to remain invariant, A has transformed in a very particular way, such that this derivative transforms covariantly. So under psi prime transformation, d of psi also transforms, and it transforms by simply, we argued yesterday that this transforms into that. Psi prime becomes, of course, u psi. So these u inverse and u cancel out, and you get dux, ux d mu psi of x. So you see that the derivative transforms exactly in the same way. That's the way psi transforms, and derivative transforms precisely in similar way. Both of them get multiplied by u of x. Okay? For that reason, this derivative is called covariant derivative. Now, since the derivative is transforming in this way, psi bar is going to transform by psi bar times u dagger, then u dagger will cancel this u, and the whole term will remain invariant. Okay? The implication of this transformation law was that a prime mu is u a mu u inverse plus I u d mu u inverse. And f transformed in a nicer way by u f mu u inverse. So this is basically what we covered yesterday. Any questions? So when you have an action, the first thing you want to do is to derive the equations of motion. That's one of the things that you would like to do. There are two fields here. To obtain the equations of motion, you have to look at the variation of the action with respect to the variation of these two fields. Or the field equation, equations of motion, or the field equations. So let's first look at the variation of the action with respect to the variation of psi. We put psi there just to indicate, actually it's sufficient to look at one of them, and simplest is psi bar. There is nothing else where psi enters. Therefore, the psi field equation will simply be I d slash psi equals to 0. This, of course, looks only superficially simple because you know that it's a matrix equation and it has quite a lot of things in it. This term makes it a nonlinear equation, so it's hard to solve it in general for arbitrary A. The variation with respect to A is slightly more involved, but not too much. There are two places where A enters. One is here, and the other one is here. Here, it comes through the covariant derivative. So the variation with respect to A will be psi bar. Actually, the product of two i's. There is an I here and there is an I outside. So they just give you one. This becomes psi bar comma mu variation of A mu psi. We just keep it in this form for the time being. But then there is a second place where A enters. You have to calculate that one as well. So it is -1/2. Here, this trace helps because inside the bracket, you have two terms, and you have to look at the variation of both of them. This is the only places where, in fact, all the places where A enters. It enters essentially everywhere. Okay? Now, trace helps because the trace of the product of two matrices, A and B, is the same as the trace of B and A. There is a cyclic property of trace. So using that, you can put this one in front and then raise and lower the mu nu indices. This becomes like that, and therefore this term is essentially minus 1 over E squared. The 1/2 cancels from the 2 from there, and I am going to write this as an upper index. No, I want to write the other way down. I'm going to write as F mu nu, so I want to use the trace cyclic property of trace to put this on the other side so that this becomes like that, times the variation of F mu nu. The two terms collapse into a single term. Okay?
And G mu nu does not contribute to
Which G mu nu? There is no G mu nu here.
the indices.
Eta. You mean eta? The Minkowski. But that's a constant. That's a constant. Eta is, what can it contribute? It's 1, minus 1, minus 1, minus 1. So in evaluating the variations, you should evaluate the variation of the fields. Okay?
Okay, I see.
So we need to evaluate this term. So let's do it here in order not to write everything again. Using the explicit expression of A, F in terms of A, there is a commutator term which also you should take into account in F. So that's the variation of F. But again, here you can use the antisymmetry. By changing the label of indices here, interchanging mu and nu, and using the fact that F is antisymmetric, this becomes like that. Antisymmetry of F also will change this sign into a plus. Okay, so these two will collapse to that. Likewise, when you expand this commutator, there's a nu minus a mu. In the second term, you can change the nu to mu here and there, and use antisymmetry. It becomes just like one term times 2. Okay? So the upshot is that you get 2 d mu a nu minus I variation of just one of these terms in the expansion of the commutator. And here you have to take both terms into account. So it is 2 d mu a nu minus I d a mu plus a mu d a mu. You have to be careful that they do not commute with each other. And since there's an F there, there's product of 3 matrices. You can still use the cyclic property, and we are going to use it. But you have to be careful how you are using it. So we are going to use it here, because you see that if I change mu and nu, if I interchange them and use antisymmetry of that, this becomes the same index structure here and here, but the sign changes. So using the antisymmetry of F, I can write this minus delta A mu. Still they do not commute with each other, because here delta A mu stands first and A mu second, there A mu first, delta A mu second. We want to push all the delta A mu's to the right. Okay? For that, it's simple. What you need to do is first, so let's consider just one term. So here delta A nu is on the right, here delta A nu is on the right, but here it's in the middle. So I need to massage only that middle term a little bit in order to bring it to the same in order. First I use the cyclic structure and put this there. And then I use the cyclic structure to put that there. So this term here contributes this particular combination, and delta A nu will be on the right. Here it's on the right, here it will be on the right, and there it's on the right. Here I will do an integration by parts, so that will bring a minus sign and put the differentiation on F. Remember that we are looking at the integral of this, so you can do an integration by parts. Sorry, there was also a 2 here, I forgot, no? Everywhere there is factor of 2. So this 2 we can take out. Let me put it outside. Doing an integration by parts will make this minus d mu f mu nu. There's a trace always. Should not forget that. That's important. Times delta A nu. Here, there is, first of all, there's a minus I. Inside the bracket, for that term, I have to put this with minus sign in front. F mu nu A mu F mu nu, and here it is just F mu nu comes there, A mu, and there is a delta A nu standing in front of it. And this is a nice commutator standing here. So this is minus the commutator of A mu F mu nu. So the final expression then becomes a trace of minus d mu F mu nu plus I, the commutator of A mu F mu nu times delta A nu. That's what we obtained from the variation of this term. Let's put everything together and construct the variation of the action under the variation of A. So the variation of action then becomes d for x. There's this term coming from the first term, psi bar gamma mu variation of A mu psi. If you also call this mu in order to make it to have the same index as this term. And from here we have a minus 1 over e in front, times the trace of this expression minus d mu f mu nu plus I a mu f mu nu times delta a nu. This trace acts, of course, in the whole thing, and we need a lot of brackets. So that bracket closes here. So let me reset. No. I should put it like that, and that's like that. I mean, so this trace is acting on everything. So there is one bracket here, there should be one bracket. Okay, now it's okay. So there's something inside here. Let me give it a name so that I can remove some of these brackets. I will call it d mu f mu nu. And of course you will see that this d mu is a covariant derivative. So d mu f mu nu is the name of what is inside, namely minus d mu f mu nu plus I a mu f mu nu.
There is a factor of 2.
There is a factor of 2 both there and there, so there should be a factor of 2 in front of everything. Thank you. So, one more line. Let's also multiply this minus inside. So this I should have called minus d mu. And then it will be like this. So therefore this is plus 1 over e trace of d mu f mu nu delta a nu. Now there is no need for so many brackets. Okay, so that's the d mu nu is given by here. This is definition, which came out from the variation of the action. Any questions?
We have to the whole thing or just to the trace? We have factor of 2 to the whole
So
thing.
there's trace is acting on that, and the factor of 2 was here only. Yes, thank you. But it was only here. Yeah. So here also, very good. It's only here. It's okay now? I think it's okay now. Okay. So the next step is to just substitute the matrix A in terms of its components, because we want to identify the coefficients of the vector potential A. So that's psi bar comma nu tau A psi. You can put delta A nu A there. These are just functions, so you can just put them outside. The matrix structure of it is here on the taus. And here it is 2 over E trace of this object. So let me first show something about it, and then so I'm going to come back and write this second here. But before doing that, let's just work out this derivative in terms of its components. You see that the first term is just the ordinary partial derivative. So the derivative, of course, these taus are constant matrices. It will be simply that. The second term will have A mu B, F mu nu C, the commutator of tau B tau c. Substitute for a mu b tau b, or f mu nu c tau c, and then these are functions, they come out of the commutator. The only commutation is this matrix, and that's plus I epsilon b c a times tau a. Okay? Therefore, we will write this as f mu nu a times tau a, where f d mu f mu nu a is whatever you see here, d mu partial d mu f mu nu a. There's I here and minus I there, so that makes it plus. There's epsilon bca, which you can write as epsilon abc in the natural order, delta mu b and f mu nu c. These are the components of the covariant derivative of f. So here I can therefore substitute 2 over e squared trace of d mu f mu nu a delta a mu b tau b tau a tau b. The trace will hit only these tau a tau b, and it's produce 1/2 of Kronecker delta ab, 1/2 will cancel the 2, and the Kronecker delta will turn b into an a, the label here. Okay, so you can factor out this factor delta a nu there, and so this whole thing, this is the trace is acting here, and this is 1/2 of delta ab. You see what I'm writing? Delta AB with this will turn it into delta A nu A, and that will be the common factor. So the offset of all this will be d for x psi bar tau a psi plus 1 over e squared d mu f mu nu a multiplied by delta a nu a. And if you set the coefficient of delta a nu a to 0, you will get the field equations for the a field. Yeah.
When we take the commutator of a mu with f mu nu,
This?
yeah, this one. How we?
So this one. So that's a mu b. F, that's a nu b tau b. F mu nu c tau c.
Yeah, but we write at the end f mu nu a to be with three terms.
No, we just keep it as this. So it's a matrix like this. F, you can write F always as F mu nu C tau C.
I see.
That's what I'm doing. Just substitute this and that. You don't need to expand this F again in terms of A. That you don't need. It's a 2 by 2 matrix, and you can write it like this. And we know what this is because we already worked it out.
Okay. But the problem is in the last term we have only a b, we have different indices. We have tau b, tau c, not tau a. We can factorize the a from here and here, but here we will have.
But this is F. I'm not going to write F like this. I'm going just to give it as F. Here I'm not writing F in terms of its components, in terms of A. I'm just keeping it like this. So from here you see that since these are functions, you can put them outside the commutator here. The only thing which remains on the commutator are the two tau matrices. and the commutator gives you this. Okay? Okay, so is this clear? So this changes this current delta A times that gives you simply 1/2 of delta A mu A. This times that current delta. And that 1/2 eliminates the 2, so the whole thing eventually becomes like this, and delta A mu is the common factor in front of everything. Therefore, if you set that variation of delta A to 0, you get the equation of motion for which are the generalization of the Maxwell's equations. And they become d mu f mu A equals to minus psi bar tau h. Sorry. Did I?
Gamma no missing. Gamma no missing in the first.
Oh, come on, yes, come on. Thank you. Otherwise, the indices wouldn't match. Which we are going to call it, sorry, plus or minus J nu A. You remember that in Maxwell theory, you didn't have that matrix there, you had only one, and that was the current on the right-hand side. And here you had the ordinary derivative, not the covariant derivative, okay? But since A is self-interacting, remember that this d mu has an A in it, and F itself is nonlinear in A. These are in terms of components. So this, the left-hand side is highly nonlinear in A. In Maxwell's theory, it is simply d mu f mu nu, and f mu nu is linear in A. So the left-hand side is relatively simple in comparison with this one. This one is very nonlinear equation. It's more similar to gravitational field equations rather than Maxwell's equations. I mean, it's similar to both of them, but also it has similarities to gravitational field equations. Okay? Furthermore, in the Maxwell's equations, you simply, so in Maxwell, in Maxwell, you have d mu f mu nu equals to j nu. In comparison with that, so minus j nu. So the Maxwell corresponds to the case that you set this one to 1 and drop the nonlinear terms on the left-hand side. And this immediately implies that if you need another d mu on both sides and use antisymmetry of F, tells you that the current should be conserved in the sense. Okay? Here, we have a more complicated situation because the derivative is not the ordinary derivative, and if you act with another d mu, you have to find out what the outcome is. And you can evaluate it. One of the exercises in the notes tells you that actually this is 0. This has been left to you to show in the homeworks.
So is this a conserved current then?
It is conserved, but the conservation involves the covariant derivative, which implies that you cannot use this current to construct the conserved charge. Here, you use this conservation to construct conserved charge. But there you cannot do that, because the derivative is not an ordinary derivative. You remember that in constructing conserved charge, you had to use a theorem converting a volume integral into a surface integral and then getting rid of. I'm saying that the fields will vanish at infinity, therefore the charge is conserved. But here, you cannot do that trick anymore, because this is not an ordinary. This involves gauge fitting it. Okay? So therefore, you will not get the conserved current. It's covariantly conserved, but you will not get the conserved charge from it in the ordinary sense. On the other hand, the F mu nu can be written as, in terms of components, here. And the first term will involve just the ordinary derivative. So if you expand this, if you substitute for F mu nu in terms of its components and expand the whole state, then it will involve, there will be a partial derivative acting on that, plus extra terms. Those extra terms you can shift to the right-hand side and define another current, which will be this one, plus the contribution coming from the self-retraction of the gauge field. And if you hit with an ordinary derivative, you will get 0. That means expand this equation and write as d mu F mu nu A plus other terms. There will be other terms there as well. Okay? So the other terms actually, I wrote it there, so let's just write it. So the other terms are these. Plus epsilon A B C A mu B A mu C equals to minus J nu A. Now you can shift this to the other side and write it in a form which looks, the left-hand side looks rather similar to the case that you have for Maxwell. I need to erase something. Let me erase this part. So this you can write as d mu F mu nu A equals to minus J nu A minus epsilon ABC A mu B F mu nu C. If you hit with the d nu, the left-hand side has to be 0. Therefore, let's call this like this, minus G A nu. And from here, it follows that d nu G nu A equal to 0. So you get an ordinary conservation law. Not the covariant derivative, but ordinary partial derivative.
If you try to find another current, then it will be this second one.
Right, that's the exercise in the notes. So here you can, of course, you can obtain conserved charges, but they will not be gauge invariant. Okay? This is also very similar to gravity. You have the same thing. You have problems in gravity in defining the invariant or covariant energy momentum tensor. It's very similar to gravity. I mean, you haven't gone as far as in your course in general relativity. Probably you haven't reached that stage yet to be able to see that, the similarity or the analogy. There are plenty of analogies between the Abelian gauge theories and gravity. And anyway, I mean, people have studied these things a lot, but I do not want to stop on it at this stage because we are not going to use it immediately. Just wanted to point out that this generalization from U1 to non-abelian gauge theories has interesting aspects to it. It does not just go from one group to the other, but it brings in a whole lot of new things. Now, the derived equations of motion, for the time being, we are not going to use them. In fact, we will hardly use those equations. Maybe, yeah, okay. I don't think we will ever use them. In the U1 case, we may use them, but not for the non-abelian case. And I want now to go to the second part, namely the generalization of what we have done so far for the SU2 and doublet representation, unless you have questions.
There should be an E squared there.
Thank you, yes, I forget that. Where is that E squared? Yeah, okay, so it should be in front of us there. It comes from there. I mean, why is it E squared and not E? Okay, let's leave it there. That's strange. If I had the E there, then this would be the current would be multiplied by E. Now it's multiplied by E squared. I know I got something. Okay. So let's move to the next topic, which is step-by-step generalization of what we have been doing. The first thing is that there is nothing special really about the doublet representation of SU2, although we will see that it is important for the standard model, but for the general argument and general construction, you could have started from any representation of SU2. Okay? So let's keep G again, SU2, but assume that psi is in some other representation of SU2. And you know how to characterize any irreducible unitary representation of SU2. It's characterized by what? Yeah, by an integer or half integer positive or non-negative number. So this belongs to, let's say that it belongs to a representation with spin J, a representation. This spin has nothing to do with the space-time spin. It has to do with SU2. Spin K, let's call it K. So what will be the dimension of this representation? 2K plus 1. So dimension will be, dimension of representation will be 2K plus 1. This means that the generators of SU2 will be 2K plus 1 times 2K plus 1 Hermitian matrices. So the TA, the three generators of SU2, of course, the number of generators does not depend on the representation. They always remain. They are 2K plus 1 times 2K plus 1 matrices acting on the subside. So in order to make it a little bit different from what we're doing for the doublet representation, let me denote it by capital U. It will be exponential of I theta AX TA, where the TA will be this large 2K plus 1 times 2K plus 1 matrices. If K is large, J will be large. Okay? And psi prime will be obtained from psi if you do a transformation in this way. So we want to construct a gauge invariant action for this field, which belongs not to doublet but to an arbitrary representation. Of course, the only step which was involved in the construction was the construction of the covariant derivative. The action, of course, always will look like this. Let me, the gauge field part, let me write it in terms of components so that I don't have to talk about normalizations of generators, etc. Just 1 minute here. So the gauge action, you remember that gauge action was d4x trace of f b nu, and if you write this in terms of the component fields, it will be trace of tau A, tau B. This is 1/2 delta AB, Therefore, the whole thing will be minus 1 over 4 e squared d4x f mu nu a f mu nu a. Okay? So that part remains the same. There is no trace now. We will simply write f mu nu a f mu nu a.
Is it independent of representation? That's
This structure is independent of representation. What can depend on the representation is this trace, because the normalization can depend on the representation. So you have to normalize the generators in some way. We do normalize it in such a way that this remains always in this form.
But is the chronicle delta also independent of representation?
Yeah, of course. Current curve is delta AB.
As a
I mean,
result,
so if you take these representatives, the general thing, of course it will be always proportional to the current curve delta, but there will be a number there.
the constant changes, okay.
Okay? It has to be an invariant tensor. SU2 does not have any of the invariant tensor.
But it could have.
It has also, of course, epsilon, but epsilon is rank 3 and, or rank 2 is epsilon AB, but this has to be symmetric. So we will keep the gauge action always in this form. Now, the only thing is, how do we define d slash, or rather d mu? In the SU2 case, in the doublet representation, we had it like this, and this was a 2 by 2 matrix constructed from tau A. But the tau A's were the generators of SU2. So all you need to do is now put A there and put the generators, the corresponding generators in the representation. Nothing will change. The principle was to demand that d prime mu is ux d mu ux inverse. Now, since A is in this representation, the matrix has the same dimension as the representation, that means as the U, therefore this whole thing makes sense, and the transformation property will formally look the same. The message will be larger. But if you write in terms of the component A mu A, you will obtain the same expression. Okay? Is it clear? So the only thing is that in the particular case that we were considering, these were given in terms of Pauli matrices. In the larger case, there will be bigger matrices. You can work out, you know how to construct the generators of this SU2 in any representation. Start from highest weight states and then act with the raising, lowering operators, etc. Clear? Any questions? So this is the first generalization, to go from the doublet representation to a large representation, to an arbitrary representation. You have questions? Okay. The next thing is to introduce also scalar fields. In the standard model, we have spinors, vectors, and scalars. But that's also easy. Everything just is how you define the covariant derivative. So take a bunch of scalars phi, which transforming in a representation characterized by k prime. And denote the generators in this representation by capital TA, for example, and then define the covariant derivative of phi as d mu minus I a mu a TA acting on phi. Okay? So you can add one more term to this action. The covariant derivative will transform always in the same way, except that this u will be now in that particular representation. It will give the same transformation law for A, and you can add one more term to this action. Which will be manifestly gauge invariant. Scalars can have mass terms. In fact, they can have also the potential term like phi dagger phi squared.
When you mean scalar, it's Lorentz scalar.
They are Lorentz scalars, but transforming non-trivially under the gauge SU2.
It has an index A,
Nothing
2k
else.
plus 1 indices.
2k prime plus 1 indices of SU2 and no other index. Unlike the spinors. Okay? So when I say scalars, it means Lorentz scalars here. But obviously when we say that it belongs to a k prime, spin k prime representation of SU2, then they are not scalars with respect to SU2. Transform in some way. But if you have fermions and scalars, depending on the type of representations they have, you can also add extra terms called Yukawa terms. So they will have their own coupling, Yukawa couplings, and this term that if you can add or not will depend on the type of representation. So in general there will be a matrix there, scalars there, and some other fermion here. I have given an example of this in the notes, and today if you wish to consider a standard model, then I will give another important example of it in the standard model. These terms are very important in the standard model. But this term depends on the type of representation. So let me not give an example here because there's one in the notes, and then I will give a sort of example of which is very important for the standard model. This all you can do essentially with SU2. To have fermions, scalars, and the vector fields, and this is practically the most general Lagrangian you can construct, which does not have negative mass dimensions. Okay? Every term has positive mass dimension.
We put mass term for scalar fields. Should we include it? Because for
The mass term should be there.
For spinors we didn't put. So
Because the mass of the spinors, in fact, that's the reason why you have this term there. The mass of spinors, as we will see later, let's come back to this question after I explain the next thing, okay? If there's still a question, then I will discuss it there. The mass will come from here for the spinors. So, can I erase this? Now we want to go to arbitrary groups, not just to, so far we were playing with SU2, but we want to go now to some other group. So G, any compact Lie group. It can be the product of several factors, or it can be just one piece, like ON, SUN, or whatever. Okay? And we take psi in some representation, some unitary, let's take it also irreducible, because whatever is reducible you can compose into irreducible pieces, reducible representation of G. So let's assume that's an n component representation. So its dimension is dimension of representation. Let's call it n. It's a unitary representation. Again, we want to construct an action involving this field, and which is invariant under local transformations of this group. So psi prime goes to psi goes to psi prime x, which is given by some matrix in this representation. I have to give it a name. I hope you will not be confused with what I was writing there. I mean, I'm just writing u of x psi of x, where this u is a unitary matrix and it is n by n. So if you denote the generators by TA, A will go from 1 to what? What will be the range of the A if TA are generators of G? For any group G. Dimension of G. For SU2, dimension is 3, so it goes from 1 to 3. If you take some other group, then it will go as many, you will have as many generators as dimension of G. Okay? And the representation is n by n, therefore these are n by n matrices, and they will satisfy the Lie algebra of the group. Where these are the structure constants.
What's that? U
Minus. So for SU2 they were just epsilon ABC, but in general they will be more complicated. And the T's we assume Hermitian.
So we dealing with SUN.
No,
No.
with any compact group. Anything. It could be SUN, ON, G2, E7, E6. There are plenty of compact groups. SUN is one example, but this doesn't have to be SUN. All compact groups have finite dimensional unitary representations. Any compact group has finite dimensional unitary representation. You haven't seen these things in group theory first? Okay. So, by now you know what to do. You need to construct a covariant derivative. It will be the ordinary derivative minus I A mu A TA psi. And then run the machinery again. We just go through, and the action, which will be gauge invariant, will be psi bar I d slash psi minus 1 over 4 F min u A, F min u A. The range of A now will go from 1 to dimension of the group. Okay? It will be different. And if you have psi, scalars in some representation, then you can also add scalars. Depending on the representation, you have to add these things and possibly you coterms, if they are allowed. So this is the general scheme. The general scheme is whatever transforms covariantly or in some representation of the group, you define a covariant derivative, which is the ordinary derivative plus a connection term, plus a gauge field term. Okay? And this gauge field is always in the Lie algebra corresponding to that representation. For example, here we have the covariant derivative of f. We already saw that f transforms in the adjoint representation of SU2 in this particular example. In fact, it transforms for any group, it transforms always in the adjoint representation of the same group. Because the A that I'm writing here, you see that A is in that adjoint representation. There are as many A's as the dimension of group, that's multiplied by its generator. So this formula is general, the formula for F min u, which I erased. Going through the same scheme, you will find the same definition of F, except that Now, A and F are in the Lie algebra of this arbitrary group G. A is a new ATA. Likewise, FB new will be FB new ATA, and if you substitute these, you will get FB new equals to D mu A new A minus D mu A mu A, and here instead of the epsilons, you will get the structure constants of the group. F A B C, A mu B, A mu C. Nothing will change, no? Whether you have here tau or t, it doesn't make any difference. The only difference comes when you come to the commutator, and then the structure constants will be different. Okay? And therefore, the covariant derivative, since this always transforms covariantly, you can define covariant derivative of f using the same principle. As an example, here you see that we said that f transforms in the adjoint representation of SU2. So its covariant derivative is the ordinary derivative plus a term in which comes from here, in which A is multiplied by the matrices in the adjoint representation. The adjoint representation of any compact Lie group is given in terms of the structure constants. So in the adjoint representation, F is always in the adjoint representation. TA BC equals to I times F BAC in that order. In the particular case of SU2, these are epsilons. Okay? So if you follow this principle to construct covariant derivative of F, you should write d mu F mu nu equals to, okay, so if you want to construct the A's component, it's d mu F mu nu A minus I times A mu B T B A C times F mu nu C. I'm writing this in matrix notation. So if you wanted to construct the component R here, you should take RS S. That's the, in terms of components, it would look like that. It's clear? This is matrix, column matrix. R ranges from 1 to dimension of the representation n. So let me explain this. I see that you are puzzled. So this is a matrix equation. This equation. So the equation was, when we write d mu psi equals to d mu psi minus I A mu times psi, you remember that psi is an object with very many n components. It's a column matrix with n components. So you can ask, what is the r's component of this expression? This one is simple, you just put the r there. But here you have the product of two matrices. So you have to put A mu rs psi s, matrix multiplication. What's A mu? A mu is A mu A TA rs psi s. So the matrix elements of the generators into there. Now, F mu is the analog of the psi. It's the analog, I mean, it's not famous, nothing like that. For us to construct covariant derivative, the important thing is the transformation property of the field, not if it is fermion or bosons or what. Okay, for this, the only important thing is that what's the transformation property of this field. Say that it transforms in the adjoint representation. So therefore, here you have to put the generators in the adjoint representation. The generators in the adjoint representation, we said that given by F, A, B, C, F mu nu C. So this I times that I becomes plus. Therefore, from here you see that d mu F mu nu A is d mu F mu nu A plus this term with the structure constants. Okay? It's ABC times A mu B F mu nu C plus F ABC times A mu B F mu nu C. That means this covariant derivative of F is constructed exactly the same principle that we use to construct covariant derivative of any object. That's not a new definition. It just follows the general construction. The only important thing to construct a covariant derivative is to know in which representation the object transforms, because to construct the covariant derivative you need the generators of the gauge group in that particular representation. Yeah.
And the first one is covariant. The last equation.
Sorry? Yeah.
In the last equation, the one
Yeah.
box, yeah, the first one is covariant derivative.
This covariant derivative. I'm sorry. Yes, thank you. Any question on this? So we have one construction, and that's the construction of covariant derivative for anything transforming in some representation of some group. It's the same principle which is applied for F, applied for psi, applied for phi. The only thing which changes is the representation of the group.
For the general definition of F mu nu, we at first assume that commutator of covariant derivative.
The same definition works for everything.
Like it's more defining.
Yeah.
And
Any group, I mean, if you go back there and see what was involved, the only thing was that the metric structures were just the taus. Replacing tau with some other matrices for some other group. Wherever you see the commutator of two taus, you have epsilon. Now the commutator of two taus will be the structure constants.
But at first we always maybe hiddenly assume that the gauge field will come from some F mu nu, which is defined as that commutator.
No, the F mu nu comes from the gauge field, not the other way around. The F mu nu is constructed from the gauge field. The gauge field is not constructed from the
So the gauge field means that that commutator should equal F mu nu, like the.
Right.
Okay.
So that definition, that d nu equals to minus I F mu nu is general. So if you substitute for this d mu, the definition that we gave here, for example there, and calculate this commutator, you'll get the formula for F mu nu for any gauge group.
And this was the reason that F mu nu transforms in adjoint.
Right.
Is F mu nu and K mu have to transform the same representation?
No, A mu transform, the index that A carries is like the index that F carries. But we saw that A does not transform like F. In transformation of A, there are two terms. The first term is like the transformation of F, but then there's a derivative term, U d mu U inverse.
Right.
Okay? So therefore, the transformation is different. So you cannot define covariant derivative of A because it doesn't transform covariantly. You can define covariant derivative of objects which transform covariantly. A doesn't transform covariantly. It has a covariant piece in it, homogeneous piece, and then there is an extra term which involves the derivative of the transformation matrix. It's like in general relativity, you have the critical symbols. You have seen that, no? Not yet. Connection components. Okay, so finally we come to a realistic model, and that's the last topic that I want to discuss and stop. But I think we can do it in 10 minutes. So far I have been assuming that the fermions are Dirac spinors. But you know that there are spinors which have only 2 components, not 4 components. And these are called the wire or Kyr spinors. Have you heard that? You know it from your course in particle physics, perhaps, right? So, if you start from a Dirac, so Kyr spinors, you must have seen this in relatives to quantum mechanics.
Yeah.
So you start from a Dirac that has 4 components, and then you have gamma matrices. You define a gamma 5, which is I, gamma 0, gamma 1, gamma 2, gamma 3. This gamma 5 has important property that it anti-commutes with all the gammas. That's a very important property. Also, you can check that it squares to 1 and it's Hermitian. Not all these gammas are Hermitian. If you choose this, the 3 of them can be Hermitian, but then the other one will be anti-Hermitian. But gamma 5 is defined in this way, will be Hermitian and will have this other property. Therefore, since it anti-commutes with 2 gammas, with 1 gamma, then it will commute with the product of 2 gammas. So if you have gamma 5, gamma mu, gamma nu, actually this commutator will be 0. You can derive this easily from there. And you know that the generators of spinor representations are constructed from the commutator of 2 gammas. Since gamma 5 commutes with the product of 2 gammas, therefore gamma 5 will commute with the generators of the Lorentz transformations in the spinor representation. You know that if you find a matrix which commutes with the generators of the group, you can use it to reduce the representation into smaller pieces. Because psi under Lorentz transformation transforms like exponential of I omega mu nu divided by 2 times sigma mu nu times psi Therefore, gamma 5 times this, because gamma 5 commutes with sigma mu nu, therefore it will go through this term and multiply psi. So if you construct 2 pieces defined by 1 plus or minus gamma 5 divided by 2 times psi, these pieces will transform independent from each other. So psi plus and psi minus will not mix. Psi plus will transform to itself, psi plus will go to psi plus, and psi minus will go to psi minus. Okay? You see this? These are called projection operators because they project from psi into psi plus or psi minus. So every psi can be written as 1 plus comma 5 divided by 2 times psi plus 1 minus comma 5 divided by 2 times psi. The comma 5 plus and minus will cancel each other, and 1/2 plus 1/2 will give 1, so it's the same thing. That means psi plus psi minus. Now, these have 2 independent components. The psi itself has 4 components, but this has 2 independent components, and that has 2 independent components. The easiest way to see that is that if you choose the matrices such that comma 5 becomes 1, 1, minus 1, minus 1, and 0 everywhere else, then 1 plus comma 5 divided by 2 becomes 1, 0, 1, 1, 0 everywhere, 0, 0, and 1 minus comma 5 divided by 2 becomes 0, 0, 1, 1. Okay? So this times psi will project the upper 2 components, and this times psi will project the lower 2 components. And comma 5 always can be brought into this form because of, I guess you have seen these things before, right? So I don't. So we can treat them independently. This is what I wanted to derive from this. Treating them independently means that you can put them independently into representations of the gauge group. You don't have to put the whole 4 components into the same representation. You can put psi plus in some representation and psi minus into some other representation. So let's take the gauge group to be this time SU2 times U1, the product group. Let's consider a psi minus object, which we are going to write in the suggested form, mu and E, and we will put L here. L refers to the fact that this psi minus is an eigenstate of comma 5 with eigenvalue minus 1, and psi plus is an eigenstate with eigenvalue plus 1, as you can easily see from here. Okay? So this convention, we call them left-handed. So this is 1 2-component spinner, this another 2-component spinner. And this whole thing transforms in the 2-dimensional representation of SU2. So there are 2 2-component spinners. We are put into a doublet of SU2. Each one of them is a 2-wide spinner or chiral spinner. So we have put them into 2-component of this gauge group SU2. Okay? They can also carry a U1 charge. So we will call the U1 charge of it YL. We will come back to it later on. That means that if you wanted to find a covariant derivative of this object, it will be, as always, the ordinary derivative minus I, the gauge fields of SU2. We are going to denote the gauge fields of SU2 by W. Not by A, but by W, as it's customary for the standard model. And then we should put the generators of SU2 in the doublet representation. That's what we have been doing. We call them tau A. So it's exactly like what we were constructing. That takes care of the SU2 part. But it also transforms non-trivially under U1. So we have to introduce also a gauge field for U1. We are going to denote it by Z mu. And there for U1, you remember, we put the charge here. YL times psi minus. So this object under SU2 times U1 transforms by in this way. that's its explicit transformation property under SU2 cross U1. This acts on the doublet indices of psi minus, and this acts only as a phase in each one of these fields. So having constructed the covariant derivative, you can construct the action involving this covariant derivative. Okay? Now we want also to introduce a psi plus, which we are going to denote as E or E right. This has an eigenvalue +1 under gamma 5, and we want to declare it that it is a singlet of SU2, but it has a YR charge under U1. So the covariant derivative of psi plus, so let me put it here, d mu psi plus will be rather simple, because since it's singlet of SU2, it doesn't transform under SU2, you don't need a gauge field for SU2, but it transforms under U1, so you have to put a U1 gauge field. Right? It couples to this Z mu. This we denote as U1, and this is SU2. Having constructed the covariant derivative, then you can write down the kinetic energy term. That's kinetic energy term for that. And then, of course, you can also add the gauge kinetic terms for each one of them. So we are going to denote this as, let me just put it as E2 squared W mu nu A W mu nu A minus 1 over 4 E1 squared Z mu nu A Z mu nu A Z mu nu and Z mu nu. E1 and E2 are the coupling constants of SU2 and SU and U1. W mu is constructed from this gauge field in the same way that we constructed F from A. I just change the notation a little bit. W mu nu A is d mu W nu A minus d mu W mu A plus epsilon ABC W mu. This is exactly the SU2 that we were doing before, and Z mu nu would be just U1 field distance with U minus d mu Z mu. Okay. Now, in addition to these, in the standard model, there is also a scalar field. So, the Higgs field. So there is a scalar field phi which transforms in the doublet representation of SU2, and it has a U1 charge Y phi. Again, as soon as you say what's the representation content, you can immediately write down what's the covariant derivative. write down the covariant derivative, the only thing that you need to know is what's the representation content of each field. So you can add a term also, or the terms for phi field in the Lagrangian. Okay? Finally, having got all these fields, you have the possibility of adding one more term, and I have left no space for myself to add this most important term here. So plus, let me call it Yukawa term. And I will write it here. So Yukawa term is, first of all, this is a doublet. The only other, in order to be able to construct the coupling of fermions with the scalar, you need also a fermion in doublet representation, some representation of SU2. Otherwise, you cannot construct it. So we have a fermion in doublet representation. Therefore, you can write a term like psi bar minus times phi. As far as SU2 is concerned, this will be an SU2 invariant term. Also, the more doublet representation is like psi dagger phi, and that's an invariant inner product in SU2. But it cannot stay like this because you cannot add it's just one power of fermion interaction. Okay? And also, it will not be U1 invariant unless Y phi is exactly the same as Y minus. But we have another fermion, namely psi, which is a singlet. So if you multiply by this psi, the SU2 structure will not change because this is a singlet of SU2. But now the fermions have been taken care of. You can multiply psi bar times psi plus times psi minus. Then you have to add the complex conjugate of it, because it's not real. You know that the Dirac mass term is written as m if you write in terms of the chiral components. It's like this. Have you seen this before? Okay. So that's precisely the same thing, except that instead of the master, you have a two-component matrix to eat up the two-component index from psi to construct an SU2 invariant. Of course, this should come with a coupling constant called Yukawa coupling. But one more thing. Unless Y phi and Y plus and Y minus are not chosen in an appropriate way, this will not be U1 invariant. Yeah? Because under U1 transformation from this factor, so under U1 from this factor, we wrote, in fact, the transformation property of that field here. So you'll get an exponential of minus I by L on psi minus. But there you have psi bar minus. Therefore, you will get under U1, there will be exponential of minus I y minus coming from here. Why did I put where did I write the transformation law? Oh, it's here. Okay, when you complex conjugate it, that becomes minus. Then from this, you will get plus I by phi, and from the other one, you get plus I plus y plus times alpha of x. That's what will happen to this term on the U1 transformation. And in order for it to be invariant, this number has to be 0. So y minus plus y phi plus y plus must be 0. And
No, minus y. Minus.
minus. Thank you. And for reasons that, of course, you will see in the standard model in detail, it turns out that the correct choice is 1/2 here, minus 1 there, and plus 1/2 here. That means y minus is minus 1/2, y phi is plus 1/2, and y plus is minus 1/2. So that if you sum up these numbers, you get 0. This will ensure that the electron has charge -1, etc. Under the after some other things happen. I'm not going to explain because there's been an entire course on it. But this is the Lagrangian of the one family of leptons in the standard model. This is the electron family. That's left-handed electron, that's its corresponding neutrino. That's the right-handed electron. And the Lagrangian is given here. The people who construct this Lagrangian, of course, got the Nobel Prize for it. It was Weinberg, Salom, and Gleschel. Their job was to construct that Lagrangian. And it took a long time for people to work out this. This was not an immediate thing. And it took more than almost 20 years, or 17, 18 years, eventually to come up with this Lagrangian, which explains in a unified way the interaction of charged particles electromagnetically and also the weak interactions, the weak and the electromagnetic interactions. It's called the electroweak theory, the unified electroweak theory. Okay. So,
This master needs